Welcome to the final video in graph analysis where we talk about resilience. Resilience is really important when we consider graphs in real life because it measures a network's robustness or ability to maintain connectivity after nodes or edges are removed. So we differ normally between two different kinds of disruptions. One of them is a random failure. So a node or an edge gets removed randomly. Every node has the same probability to get removed. So with that, if you think of a real-life network, that would be simulating natural or accidental failures. It's just the same probability for every node to fail. However, we can also have targeted attacks. Here we have high centrality nodes or edges are removed. So the more important a node or an edge is, the more likely it is also to fail. And therefore, we can simulate deliberate attacks on the graph. Especially in information and transportation networks, those aspects are really important. This is also the aspect why really important nodes or edges in real-life graphs and networks have several layers of security for power failures, for example. There's not just one backup generator at Heathrow Airport or at Frankfurt where the really important fiber connections for your internet are going through. No, there are several backups because you want to avoid the random failures which can happen to keep the graph and the network functioning. And we can calculate resilience in networks in different ways. So we have to choose a resilience metric. So in this case, we pick, for the example only, the size of the largest connected component. You can go to pick any other graph analysis tool that we have used earlier and introduced earlier and compare them once we have failures. Because what we're doing in the next step is we simulate those failures. We randomly or target high centrality nodes and remove them. We remove them and see how the metric has changed now that the graph looks different, and then we compare that. And that is actually all we're doing. And as I said, in this example, we take the largest connected component as the metric of consideration. We have an initial adjacency matrix where the largest connected component is 6. And you always know, I show you the adjacency matrix for completion, but we also look at the graph themselves. So we have this connection here, 6 nodes. We have 7 edges, and what we're going to do now is we pick node number 3 and remove that, so it's gone. So the adjacency matrix changes. We have a modified adjacency matrix. Now the largest connected component here is 4. And we then calculate the change or the resilience of the largest connected component initially with the new one. And what we see here after removing node D, the resilience of the network is 0.67. And this is just for the resilience of node 3. What we can do, and quite often do in real life, is we go over every node and calculate the resilience there, and then take the average, for example. That's an easy way. Or we multiply every resilience aspect that we here just calculated and weigh that with the probability of failure. So if we know that a node is, because of its exposure to nature or something like that, is more likely to fail, then it has a higher probability, and we have to take that better into account to analyze the resilience of the whole graph, to understand how to make networks more robust to accidental or targeted failures.